Okay, so now we're looking at section 8-5, and we're going to look at what are called determinants and what's called Kramer's rule. And again, our goal in all of chapter 7, all of chapter 8 is to solve systems of equations, and this gives us another method with Kramer's rule. So we have a shortcut for finding the determinant of a 2 by 2 matrix, and this is only for 2 by 2 matrices. Okay, so what we can do is we can do A times B and B times A. So again, going down the main diagonal and then subtracting over here. And so we have A1 times B2 minus B1 times A2. And that'll give us our determinant. Okay, so we can use determinants with a system of equations. This is called Kramer's rule. This is for a 2 by 2 matrix. Okay. And we can find our x value and our y value using these determinants. So notice that this is the determinant for these c values plugged in here and our b values there. So just like the regular determinant. And we'll denote these. This would be our d. So A1, A2, B1, B2, A1, A2, B1, B2. And then we can plug in these for whatever we're removing. So this would be d sub x. So we removed the x coefficients and replaced them with the constants, but the b's stayed the same. And then this would be dy because the x coefficient stayed there, but we replaced the y ones with the constants. And those will give us our x and our y values. And as we can see here, finding a determinant for a 2 by 2 matrix is really easy. Okay, so let's go ahead and do an example of what this actually looks like. So I'm going to set up all of my determinants first. Okay, and D, we have the coefficients of x, 5, 6, and coefficients of y. And then we'll find that one, and then let's go ahead and set up the others. For the x, the y's stayed the same, so -4 and -5. But we're going to replace the x coefficients with these ones, so 2, 1. And for the y ones, the x ones will stay, so 5 and 6, but the y's will be replaced with 2 and 1. And now we can just go ahead and find the determinant. So we have -25. Actually, you know what? Why don't I write that out? We have 5 times -5 minus -4 times 6. And that's going to be -25 plus 24 is -1. And here, down the main diagonal, 2 times -5 minus -4 times 1. And that'll give us -10 plus 4 is -6. And here, main diagonal, 5 times 1 minus 2 times 6. And that'll give us 5 minus 12 is -7. So, using what we have right here, x is going to equal, this is our d, this is dx, and this is dy. X is going to equal -6 over -1, which is 6, and y is going to equal -7 over -1. That'll give us 7. And if you were to solve this using any other method, you would also get 6, 7. Okay. So that's our first example of a 2 by 2 matrix using Kramer's rule, but we can also use Kramer's rule for a 3 by 3. And let's look at an example of that. So when we're finding the determinant of something like this, now your book does not teach this, but I'm going to show you a shortcut for finding these determinants. This would be a really long, awful thing to memorize, but this trick works for 3 by 3s, 4 by 4s, and so on. Okay, so going down the main diagonal, so that's A1 times B2 times C3 plus B1 C2 A3 and so on. And then we're subtracting, going up the opposite way. Okay. So these are all the positive. These are all the ones that we are subtracting. Okay. So let's go ahead and do an example of this. It says evaluate the determinant for the following matrix. So let's go ahead and set up these columns here. Notice here that I copied down the first and second columns again to be able to do this. So I'm going to do the same thing here for -9, -3, 1, 3, and 8. And now I'm going to go ahead and solve for the determinant. Down the main diagonal, I have, let's see, I have 4 times 3 times 1 is 12. And then 1 times 4 times -3 is plus -12. And then 0 times 9 times 8 is going to be plus 0. And then we're subtracting the other terms. So let's do this in a different color. Minus 0 times 3 times 3 is going to be 0. Minus 4 times 4 times 8 is going to be -128. So minus 128. And then 1 times -9 times 1 is -9. So now simplifying this, these two are going to cancel out. We have a 0 and a 0. And then we have -128 plus 9 is going to give us -119. And that's our determinant. Okay. Now what about using Kramer's rule for a 3 by 3 determinant? Well, it's very similar. We're going to find these 4 determinants, and then x is dx over d, y is dy over d, and z is dz over d. Okay? So we can go ahead and go through the same process there, but before we do that, let's point out a couple things here. What about if we have an inconsistent or a dependent system? Okay, so if our d value is 0, then that means the system is either inconsistent or dependent. Now remember, we're talking about equations that don't intersect, have no solutions, or infinitely many solutions is what we're talking about here. So if d equals 0, so this main determinant here, if that's equal to 0, and at least one of the other determinants is not 0. So this could be 0, this could be 0, but if this is not 0, then that means that the system is inconsistent and there's no solution. Okay. Now if d equals 0, and let's say all 3 of these also equal 0, so all 4 of them equal 0, then that means the system has infinitely many solutions. Okay? So let's go ahead and do an example of a 3 by 3. And looking at this example here, first thing we want to do is write our determinants. So I'm going to go ahead and list out d, dx, let's see, dy, and dz. So d is 1, 1, 2, 2, 4, 3, -1, -2, 1. dx, again, we're replacing the x coefficients with these, -4, -6, 3, and the rest stay the same, 2, 4, 3, -1, -2, 1. dy is going to be 1, 1, 2, and then -4, -6, and 3, and then -1, -2, 1. And then for dz, we have 1, 1, 2, 2, 4, 3, -1, -2, 1. And now we can go ahead and solve all of these determinants. Okay, so going down the main diagonal, oh, you know what, we need to copy them over. 1, 1, 2, 2, 4, 3, -4, -6, 3, 2, 4, 3, 1, 1, 2, -4, -6, 3, 1, 1, 2, 2, 4, 3, and oh, you know what? I copied this one down wrong. For dz, this last one should be -4, -6, 3. Okay. All right. So let's go ahead and start taking those determinants again. Okay. So going down these diagonals, we have 4 plus -8 plus -3. And then going up the opposite way, we have minus -8 minus -6 minus 2. And then I'll go ahead and calculate these in a minute. I'm just going to set them all up. Going down those main diagonals, we have -16 plus -12 plus 18. And then going up the opposite ways, again, 3, 4, -1 is going to be minus -12, and minus 24, and minus -12. And next one, down the main diagonals, we end up with -6 plus 16 plus -3. And then going up the opposite way, we have -12 minus -6 minus -4. Last one, down the main diagonals, we end up with 12 plus -24 plus -12. And up the opposite way, we have minus -32 minus -18 minus 6. And when we calculate all of these, we're going to get 5, -10, 5, and 20, just by simplifying all of these numbers. So that's my d. This is my dx, this is my dy, and this is my dz. And x, y, z is going to be dx over d, dy over d, and dz over d. And again, if this d was a 0, then that would indicate either inconsistent or a dependent system. So let's go ahead and simplify these. And for dx, we have -10 over 5. For dy, we have 5 over 5, and dz, 20 over 5. So our answer is -2, 1, 4. If you had used matrices, if you had used solving systems of equations, any other method, you would still get this answer. So that gives us another method to use for solving systems of equations. And this is the end of Chapter 8 and the end of Section 8-5.